Welcome back. Today we're going to explore BigONotation, focusing specifically on the idea of dropping constant factors in algorithm analysis. We'll discuss why these constants can be removed from our expressions, allowing us to concentrate on what truly matters in assessing performance. To begin, let's define once again the BigONotation. As I said earlier, Big O is a mathematical tool used to describe the upper bound of an algorithm's running time. It gives us a high-level understanding of how an algorithm performs as the input size grows, emphasizing the order of growth rather than the exact steps or constant factors involved. Now, why do we drop constants in Big O analysis? First, it's an abstraction that helps us ignore details that aren't relevant for large inputs. Constants don't significantly affect growth trends as the input size increases. Removing them simplifies our comparisons between algorithms. Moreover, when focusing on worst-case scenarios, our main concern is how performance scales with input size. At this point, please refer to the visual demonstration, which shows algorithm growth curves with constants versus without constants. Let's look at a concrete example. Consider the function t, n, equals 3n plus 10. For very large n, the constant 10 becomes negligible compared to 3n. In our simplification process, we drop both the constant multiplier and the constant term, which leaves us with O, n. This emphasizes that the dominant term, in this case n, is what really drives the growth of the function. Here are some practical examples. For the function 2n plus 5, we simplify it to O, n. Similarly, 50n plus 25 also simplifies to O, n. In a more complex scenario, an algorithm with t, n, equals n squared plus 3n plus 4 simplifies to O, n squared, because we retain only the term with the highest growth rate. In each case, only the dominant term is kept, while the constants and lower order terms are dropped. Now, let's take a look at a visual demonstration. This diagram compares growth curves of functions like 2n plus 3 versus n. Notice that as n increases, the difference between these functions becomes less significant. This visual cue clearly shows why, in BigONotation, constants can be dropped without losing the essence of the performance trend. Let's review the key points. Simplified analysis, focusing on the dominant term, makes it easier to compare and evaluate algorithms. Irrelevance of constants. Although constants might affect actual runtimes, they do not change the asymptotic classification. Practical implication. Grasping this concept is essential for analyzing and designing efficient algorithms. In summary, BigONotation is about understanding the order of growth by dropping constant multipliers and lower order terms, which highlights the performance trends as input sizes grow. I know it is a little confusing topic, but if you have any question, feel free to write your question in comment section. So on this note, I am stopping over here. See you in the next session.